All right, today we're going to talk about a basis for the image. Before we get into that, we need to first talk about what a basis is. So a basis is a set of vectors that satisfies two important conditions for your vector space. And we're going to do some examples in just a second. So the first thing it has to have is it has to have enough vectors, so it has to span your vector space. Right? You can think of this as it has enough vectors. And the other thing it has to do is those sets have to be linearly independent. And you can think of this condition as not having too many. So let's just do like a very quick intuitive example. Let's look at R2. And we might look at a single vector. And this single vector right here would just be in the x direction. Now that vector, if you span it out, it doesn't have anything in the y direction. It can't reach everything. So this is not enough. This does not span. Right? It doesn't have too many. On the flip side, if we have 1, 0, 0, 1, and also 1, 1, then in this case, we have too many vectors because what's going to happen is these vectors are not linearly independent. So for example, 1, 1 can be made up as a combination of the other two. And what we're going to get here is we're going to get a grid, but this grid's going to be very noisy and it has too many vectors than it needs. So when you finish this grid, it's going to kind of look like this. And here you have too many vectors. So this one's going to fail this condition. This has not linearly independent. And as you'd expect, R2 is two-dimensional, so we expect it to have two basis vectors. Now, another silly example might be something that looks like this. That has two vectors, but these are not the right vectors. So for example, here, if these two vectors, one of these is simply twice as much as the other. Again, you can't get anywhere in the x direction, the y direction. So in the y direction, you're stuck. And these are not only does this not span, this fails both. Despite the fact that it has exactly the right number of vectors. So these are all non-examples of a basis. Something went wrong. But what are some examples of a basis? So let's do some good examples. And one takeaway from this is that what a basis should do is it should form a grid for that vector space. So good examples for R2. You might have 1, 0, and 0, 1. That's going to form a nice little grid that you're used to. So that's going to form the grid like this. You can either move in the x direction or purely in the y direction. We can also do 1, 0, and 1, 1. So this might seem a little weird, but you can still get everywhere in the plane. There's nowhere you can't get to by moving only in the x direction or moving simultaneously in the same amount in the x and y direction. You're moving in exactly 1, 1. So you're going to move along these lines. So a basis in some sense forms a grid that fills that space that has exactly the right amount of vectors you need to do that. No more than you need, and it can get everywhere. All right, so why might we care about this? So let's do a more practical example. And I like this example because it's something everyone can kind of relate to. It's a little contrived, but that's okay. So suppose you want to buy some number of bags of chips. You have a big party, you have to buy a big bag of chips, and for whatever reason, you want 100 bags of Fritos. Okay, I know everyone loves Fritos, so we want 100 bags of Fritos. But then you get to the store, you get to the big box store, your favorite warehouse store, and they're sold not by the individual bag, but they're sold instead in packs. So you might have 50 packs, or this would be a pack of 50 of just the Doritos, nacho cheese. You might have another pack that comes in 25 of the two types of Doritos. So one might be nacho cheese, and the other one might be the second favorite, Cool Ranch. And then finally, you'll have another box that comes 20 in all three. So this one's going to have the nacho cheese and the Cool Ranch, and also 20 Fritos. Right, so now the key idea here is when you went into the store, you said, I need 100 bags of chips. But now the offering that you have to think in, you can no longer think in bags of chips. You have to think in party packs. You have to think in these particular boxes that you have to buy. So the question is, what do you do? Well, in this particular case, it should not be surprising that you should get 5 of this one. So if we want 100 bags of chips and no more, we're gonna need 5 bags of that one. But on the other hand, that's gonna give us some overbags. We have too many than we need. So what should we really do? Well, we should actually we buy 5 of those packs. We're gonna end up with 100 of each. What we should really do is we should take all those Doritos, so all these Doritos right here, and what we're going to do is we're going to repackage them and we're going to sell them off into 4 packs of those 25. So what we can do is we can write our demand of bags of Cheetos, of bags of Fritos, as a linear combination of these party packs. Now, I've never actually done this at the store, try to repackage them. I'll do it at some point. But the main point is that this right here forms a basis. This forms a basis for R3. So if you come up with any combination, of chips that you want among nacho cheese, Cool Ranch, and Fritos. So it's nacho cheese, Cool Ranch, and Fritos. You tell me which ones you want. You can come up with some way of generating that exact combination by buying and selling those party packs, because these party packs are going to form a basis. So you can get whatever combination you want as long as you're allowed to buy and sell those party packs. So this particular case, if you went 150 and 0, you would just get, what would you do? You would get one of these, one of the nacho cheese pure ones, plus 2 times the Doritos, plus 0 of the mixed bag. Okay. And if you wanted, like, for example, 100 and 0 and 100, if no one wants Cool Ranch, you would get 2 of the nacho cheese. You would sell out 4 of this one, 4 of just the Dorito ones, and you'd buy 5. And you can do this for any vector. So if we have that vector, for example, what would we want to do? Well, what will we do? We will buy 2.5 of the 20 mix pack. We're not going to mess with this one. And we're going to sell back 3 of just these. We're going to be in the hole. We're going to owe 100 of the nacho cheese Doritos. Right? How I come up with these numbers is not too terribly important, right? In fact, all you're doing is solving a linear equation. But the key thing I want to get across is that every vector you pick here, one of the nice things about a basis is because it spans and has a linear, because it both spans and is linear independent. So this first condition here is going to tell us, the first condition tells us it's always possible to get any combination you want. And the second combination tells us that the second requirement tells us that that combination is in fact unique. So because this is a basis, because this spans R3, there's 3 vectors and those vectors are linearly independent. There's a unique way to represent every vector as a combination of these. So you cannot come up with anything else. And so before we continue, let's just emphasize that key point. So the key point is that every vector in a vector space has a unique representation under a basis. So if you change the basis, of course the representation is going to change. But by representation, we mean that tells us exactly how many of each party pack or how much of each basis vector you're going to include to add together to get the vector you want, to get the combination you want. So this is a key point. This is why we care about a basis. There's a unique way to get every point that you want. Okay, so let's talk about a basis for the image. So the image, just as a reminder, if I have a matrix, something that looks like this, the image is just the set of all possible output. So the basis is going to look like, right, when you multiply a vector, that's just going to be linear combinations of these individual vectors. So in some sense, all the possible outputs are going to be some combination of 2, 0 times some amount, x, plus 0, 1 times some combination of y, plus minus 1, 1 times z. And what we want to ask is it possible to achieve every vector that you want without using all of these vectors? Can I just ignore one of them? And that's what's going to form a basis. So by definition, the image is going to be the set of all possible linear combinations of the columns. So now all we need to do is figure out which columns we don't need. So we boiled down the question as to which columns we don't need. And so how are we going to determine that? We're going to determine this by determining linear independence. So we're going to ask which vectors make the set. I don't know what happened. There we go. And what we're going to do is we're just going to go down the line and we're going to say, okay, this first vector, that first vector is in. So 2, 0 is the first one on the team, the first one on the basis, and it's going to be in. And then what we're going to do is we're going to try to add 0, 1. So for the first time that we do this, we're going to do this in a very slow manner to kind of illustrate linear independence. And at the end, we're going to kind of go with what the punchline is. So we want to check, is this linearly independent? All right, so by just eyeballing it, you can see that 2, 0 is not a linear multiple of 1, 0, and vice versa. So then, in fact, they are going to be linearly independent. But let's get a surefire way of figuring out whether or not things are linear independent or not. So keep in mind, linear independence is the same thing as saying the matrix just concatenated with all the vectors times some vector x equals 0 has only the x equals 0 solution. So what we're going to do is we're just going to solve. If we want to check the linear independence of 2, 0, and 0, 1, we're going to look at, does this equation have any non-trivial solutions? And what's really nice is almost done for us. All we need to do is to do a little bit of row reduction. And in one step right now, we're going to be given, I guess we can just turn this into augmented matrix. And in one step, we get something that says, okay, this right here, the first row tells us that x equals 0, and the second row says y equals 0. And sure, if it only has the all 0 solution, so that means that those two original vectors are linearly independent. So what that means is now this 0, 1 has made the team. It's made the basis. So now we're at 2, 0, and 0, 1, and now we want to check, does -1, 1 want to make the team? So we're going to check, does -1, 1 to make the team? Now, you should be a little wary right now because, as you can see, our vectors are only two-dimensional. There isn't room for a third vector. So before we even start, our intuition should tell us that, in fact, there's not going to be room for -1, 1. We're out of room. There's literally no more space. There's no more dimensions for -1, 1. But we're going to go through and kind of do the long method so you can see it. So we're going to check, does this have a non-trivial solution? And because there's not enough room, there is going to be a solution that's not all zeros, but we're going to figure out what that is. Let's go through it. So the first step, we're going to row reduce there. And one thing I want to point out, and I think this is very important because we're going to come back to this. This first step here was the same as before. So in some sense, when we add on another vector, we're not actually changing any of the work that we do. So you don't actually have to do this for each individual vector. You can kind of go put all the vectors together and figure out from there which vectors to keep and which ones to throw away. So we're gonna do that at the end, but I just want to point out that, in fact, the work is going to be the same up to this point. Okay, so after we do that, we're going to end up with the same vector except for this case. Let's turn it into an augmented matrix. And now it turns out we're already done. Right? We're kind of already done. We did the exact same work we did before. It's always going to be the exact same work. You have a nice staircase. You have these leading ones that fix those dimensions. You have these zeros. And moreover, you have this nice free variable. So let's figure out what this says. This top equation translates as 2x minus 1/2 z equals 0 and y plus z equals 0. This is a free variable, so that's going to be z equals z. And if we solve for x and solve for y, we can put this in geometric form. So this is going to be 1/2 minus 1 times z. Right, so this is not necessarily the solution to our problem, but I want to point out that this vector here, this is a line. It has one vector. That vector forms a basis for the line. So that vector that spans that line, that's a basis for a line. And it's the kernel, this is the kernel to this matrix. And it has nothing to do directly with our equation, but that's kind of connecting some of the dots. All right, so what does this mean? This means that for our particular question, we were concerned with linear independence. Well, when we added this -1, 1 vector, we got a free column, which leads us to infinitely many solutions, which means that vector was not linearly independent. So we can just cast that one away. So what do we have left? We have something, we have these two vectors, and these two here are going to form a basis. Right. Now, what does this basis look like? If you form the grid, it kind of looks like this. Right. And there's no reason why you have to pick these particular vectors. So it's going to form a grid with those two vectors. And again, this is going to span all of our two. So it's not actually special that we pick these two vectors. But in just a second, we're going to do a quick example where you're not going to get everything. So this spans all of our two, and this is the basis. So we picked this basis, and much like the party pack scenario, we kind of picked this because it was natural, right? The image of a matrix is just some linear combination of the columns. So we should pick the columns when we can. In this particular case, it happens to be that everything in R2 is possible with this grid, but it's these vectors that generate that grid. You could pick a different vectors if you wanted to, but you don't have to. Let's just stick with the ones that are given by the columns. All right, let's do another quick example. This one's going to be a little different. And we're going to consider this matrix. And we're going to want to find the image. So what we did before, just to kind of trace what we did before, we kind of just row reduced the whole matrix and figured out where the free columns were, and we killed so strong word, but we got rid of those. So we kind of kept the first one because the first vector is kind of almost guaranteed to have a pivot. And in this example, we kept the second one because there happened to be a pivot in the second column. But for the third column, we missed a pivot, which means that vector didn't add, the original third vector didn't add anything to our image. And we're going to play the same game here. We're just going to go along, figure out where the pivots are. Those pivots are going to indicate which vectors add to the dimensionality of our image and which ones don't. And we can describe the image. So let's go ahead and just get started. So that one's already good. We just need to row reduce this guy. Again, you might, if you want, you can write this equals 0. That's not actually too terribly important. These zeros on the right are actually never going to not be 0. But we can write them anyways. So we have those pivot. We need to get rid of these two right here. So we have row 2 minus 3 row 1 and row 3 plus row 1. So what do we end up with? We end up with 1, 2, 3, 0, 0, 0. Row 2 minus 3 times that, so we'll get a minus 7. Here we have 2 minus 8, so we get minus 7 again. This one is going to be 1 plus 2, which is 3, and we'll do 3 here. And then we can go to the next one. We got that one solid. Now we're going to go to the next column. We need to divide that one by 1/7. And finally, we're going to divide, or not divide, we're going to take row 3 and subtract 3 times row 2 to zero out these, well, that entry, which is going to zero out all of them. And I guess to make it fully complete, we also need to do that one. So that's row 1 minus 2 row 2. All right, and so now we're done. We have those two leading positions. We have a nice staircase pattern, but we also missed this column right here. That column missed a pivot. So in some sense, what's going on underneath all this algebra, what the geometry is doing is you're going through each of these vectors individually and you're asking, is this adding a new dimension? If yes, you're going to get a pivot there. And if not, you're going to miss the pivot. So now what we can do is we can take our pivot positions here and we can go back up to the top and say, okay, look, these are the ones that we want. Those are the ones that we want to keep. And we're not going to keep this last one. So the image, the basis for the image is just going to be these two vectors right here. Now, the reason I wanted to do this extra example, even though it may not add a whole lot here, but we've seen kind of how easy and straightforward it can be, is that these two vectors as a basis are going to form a grid in 3 dimensions. Right, so one of these vectors, the 1, 3, 1, which might look something like this, 1, 3, minus 1, so it might look something like that going downwards. And then the other vector, the 2, minus 1, 1, 2, minus 1, 1 might look something like this up here, kind of going up and to the left, right? This is going to form a little grid on here. But this is in 3-dimensional space. So this is a plane. When everything's done, this is going to be a plane. In 3-dimensional space. And the one reason I like to view it as just these vectors, the one reason the basis is really powerful is that when you draw it, it kind of just becomes a big hairball. I mean, it is a plane, but this is not all of our 3. So even though you might think of R3 as like the perfect nice vector space, there are vector spaces within R3 that aren't easily described as just everything. So this is an example. This is just the vector space generated as the grid from those 2 vectors. And these 2 vectors is what gives you all the possible outputs of this transformation right here. So if you're only allowed these possible vectors, right here, not those ones, sorry, these vectors, right? The only possible outputs you can get are combinations of 1, 3, 1, 1, 3, minus 1, and 2, minus 1, 2. Any combination that you add with 3, 2, 0 is already included in there. That's what the row reduction does. It says our row reduction, because we missed a pivot, it said that 3, 2, 0 is already going to lie on that plane. It's like right here. So that vector is already lying on the plane. So we don't need that vector to describe this plane. So this is a nice example of a vector space, which is not all the ambient space, but still is described by more than one vector.